Welcome to the second video for Chapter 3. This will detail the variety of math that we will need to do at the end of this chapter. The first thing that we are going to look at is calculating formula mass. This is the mass of a molecule. We will use the term molecular weight. So if I talk about the molecular weight of a compound, that is the weight or the mass of that compound. So how do we calculate molecular weight? Let's look at this compound, C4H10. The first thing that we need to do to calculate formula mass or molecular weight is to look at the different elements that make up that compound. Here we have carbon and we have hydrogen. If we go to our periodic table, we can see that carbon's atomic mass is 12.01 grams per mole. And we can see hydrogen's is 1.01 grams per mole. We're not done. So we have to account these subscripts, or for these subscripts. These subscripts tell us how many moles or how many different hydrogens are in this compound. So for carbon, we have 4. For hydrogen, we have 10. So every time we see a subscript, we multiply the atomic mass by that number, and that will give us the mass of the carbon in that compound. So here 48.04 grams per mole. And here we have 10.10 grams per mole. To find the molecular weight, all we have to do is add those together. So the molecular weight for C4H10 is 58.14 grams per mole. Usually, almost always, for molecular weight, we go out to 4 significant figures. So that's why it is 58.14. We can use that mass, the mass of a compound, the molecular weight of a compound, in a variety of different ways. One way that we can use it is known as mass percentages. So mass percentages tell us the percentage of an element that's in a compound by weight. So what do I mean by that? Let's look at number 71D in your book at the end of chapter 3. So here we have a compound, C2H5Cl. So the first thing we need to do is figure out what we're trying to solve for. What we are solving for is the percentage of carbon in the compound. So, what we want to do, what the easiest thing that we will quickly want to do is, well, we'll say there's 2 of carbon, 5 of hydrogen, 1 of chlorine, so that's 2 divided by 6, which is equal to 1/3, or it'll be 33.3%. But that is not what we're trying to solve for. So what we want to do first, the first step of finding mass percentages, is to calculate the molecular weight of this compound. So carbon, 12.01 grams per mole. Hydrogen, 1.01 grams per mole. Chlorine is 35.45 grams per mole. And so remember, we multiply by how many molecules are in the compound. Carbon, it's 2. Hydrogen, it's 5. So originally there was not a subscript on chlorine. And so when there's nothing, again, we assume that there's a 1. So 24.02 grams per mole, 5.05 grams per mole, and then 35.45 grams per mole. And then all we do is we add straight down, and we get 64.52 grams per mole. Now, to find the percent of carbon in that compound, we need to take the molecular weight of the carbon, which is 24.02 grams per mole, and we will actually divide it by the 64.52 grams per mole. And the reason why we use 24 instead of 12 is because we have 2 moles of carbon. So when we do that calculation, it will equal 0.3723, because we'll get 4 significant figures. So we'll multiply this by 100, and so the percent carbon in this compound is 37.23%. And so it's 37.23%. That is the percent of carbon in this compound. So, for more practice on calculating mass percentages, I would like you to do number 73. It has to do with ammonia and fertilizer and calculating the mass percent composition of nitrogen. This will be due on September 5th, which is a Wednesday. So, what else can we use? What else can we use mass percentages for? There's one more thing we can use mass percentages for. Let's look at number 75 in the book. So, 75 states that we have copper 2 fluoride. And it contains 37.4% or 42% fluorine by mass. So we want to know how much fluorine is in 55.5 grams of copper 2 fluoride. So this is a pretty straightforward problem. So we know we have 55.5 grams of copper fluoride, and we know in copper fluoride we have 0.3742 because it's 37.42% of fluorine in copper fluoride, copper 2 fluoride. And so when we do this calculation, we get 20.8 grams of fluorine. So there is, in these types of problems, there is many ways that we can get to this number. the 55 grams, or I could tell you a variety of starting points that you will then have to use this percentage to then calculate how much of a component of a molecule is in the compound. So to practice this, I want you guys to do number 76 for September 5th. So, this is how we can use mass percentages to tell us either how much of a compound is in a molecule or in a specific given weight. We can use compounds as what's known as molar ratios. We can determine how much of one mole versus another in a compound. This will be very important, especially for Chapter 4 when we start to do stoichiometry and calculating when we change from one thing to another. So, let's see this ratio in action by looking at number 81b. So 81b, we want to know the number of moles of hydrogen. So we want the number of hydrogen moles in this sample. The sample we're given is 1.3 moles of CH4. And so what we know is we're given 1.3 moles of CH4. We know the ratio of how many hydrogen moles are in the total compound. And so we know for every 1 mole of CH4, we have 4 moles of hydrogen, based on the subscript. And so the final answer would be for every 1.3 moles of methane, we would have 5.2 moles of hydrogen. Now, we can also carry that further if we wanted to calculate the number of atoms of hydrogen by multiplying that by Avogadro's number. But for this problem, they asked us the number of moles of hydrogen atoms in each sample. Now, does this number make sense? That we have a 5.2 moles. The correct answer would be yes, because we're starting with slightly above 1 mole of methane. So for every 1 mole of methane, we get 4 moles of hydrogen. So since we're starting with 1.3, we would expect to be slightly higher than 4. And we are. What else can we use these molar ratios to find? Let's look at number 83A. So question number 83 says that we need to calculate in mass in grams. So we want the mass of sodium in 8.5 grams of sodium chloride. So since we're calculating mass in grams, we can solve this problem one of 2 ways. There's 2 different ways to solve this problem, and both of them will give you the same answer. The first way is to do what we just learned about mass percentages. So we know the molecular weight, or we calculate the molecular weight of sodium chloride to be 58.44 grams per mole. We know sodium is equal to 22.99 grams per mole. So the percent of sodium in sodium chloride is 22.99 divided by 58.44, and that is going to equal 0.3934. We will not turn that into an actual percentage because we'll take this number like we did before when we're looking for the weight or the mass of a single element in a compound, and we're going to multiply it by the total mass given, which was 88.5 grams of sodium chloride. When we do that, we find the answer to be 3.3 grams of sodium. So that is one way we can solve this problem. So just remember the answer, 3.3 grams of sodium. So here we're going to do number 83A, but we're going to do it a slightly different way. Again, both of them will give you the exact same answer. We're going to look at the mole ratio. So, we begin with what we know. We're given 8.5 grams of sodium chloride. We know 58.44 grams of sodium chloride is in 1 mole of sodium chloride. So we've calculated that previously. 1 mole of sodium chloride is equal to 1 mole of sodium. And here we're going from moles to grams, so we want to multiply the molecular weight. So now let's check our answers. So grams of sodium chloride cancel, moles of sodium chloride cancel, moles of sodium cancel, and we're left with what we want to solve for, grams of sodium. So after we do all the calculations, remember, numbers next to each other, we multiply them together. If there's a number underneath, we then divide it. When we do this, we get 3.3 grams of sodium. Exactly the way we did before. So it does not matter how you solve this problem, you will get the exact same answer. We can also use mass for one more thing. We can use mass to determine molecular formulas. So there are two different types of molecular formulas that we are going to learn. We are going to learn the molecular formula. The molecular formula shows all of the molecules or elements within a compound. So H2O2 is a molecular formula for peroxide. But there's another formula that we can make known as the empirical formula. The empirical formula shows the smallest amount of molecules in that compound. So if we were to take hydrogen peroxide, divide everything by 2, we would get this formula, HO. This is the empirical formula. The empirical formula just shows us which elements are in a compound, but it does not tell us how many moles of those compounds are in the element. The molecular formula tells us both which elements are in the compound and how many make up that compound. So let's use mass to determine molecular formulas. So there's a variety of ways or a variety of entry points to get the mass to find an empirical formula. The first one we're going to look at is number 89A. So we want the empirical formula for nicotine. And what we are given is carbon makes up 74.03%, hydrogen makes up 8.70%, and nitrogen is equal to 17.27%. So we're given mass percentages. That's all we're given to start this problem. We need to figure out how many moles of carbon, hydrogen, and nitrogen are contained in this molecule. That will help us start figuring out the empirical formula. But we're not given a weight. If you are given a mass percent and you are not given a weight, the assumption we will make is that we will have 100 grams of sample. Because if we assume 100 grams, we now have carbon as 74.03 grams, hydrogen at 8.70 grams, and nitrogen at 17.27 grams. So if you're given mass percents with no weights, we make the assumption that makes the math the easiest. So we would assume 100 grams of the sample. So we now have carbon as 74.03 grams, hydrogen at 8.70 grams, and nitrogen at 17.27 grams. So the first thing we need to do is determine the number of moles of each of these. So if we are going to go from grams to moles, we need to divide by the molecular weight. Hydrogen. Remember, grams to moles, divide by the molecular weight. Moles to grams, multiply by the molecular weight. So, when we do this, we get 6.2 moles of carbon, 8.6 moles of hydrogen, and 1.2 moles of nitrogen. And so now that we are down to the moles, we're going to clear the board to make it a little bit easier. So carbon, we said, was 6.2 moles. Hydrogen is 8.6 moles. And nitrogen was 1.2 moles. So we can set up a basic formula. If you remember the atomic theory, we said that they have to be whole numbers. To get them to be whole numbers, we will divide by the smallest number of moles. When we do that, we get this. We still don't have a whole number, but we cannot easily turn this 0.2 into a whole number. We could multiply it by 5, but that would be huge numbers. So if you see anything around a 0.2 or below, we will just round down. So the empirical formula for nicotine is C5H7N. Now, let's say I asked you, so this is the empirical formula, but let's say I asked you what was the molecular formula of nicotine. As currently constructed, we do not have enough information to solve that. But if I gave you the molecular weight, so the molecular weight of nicotine is 162.23 grams per mole. We can use the empirical formula to find what's known as the empirical weight, which is 81.13 grams per mole. Once we know that, we can find what we need for the molecular formula. And the way we do that is we solve for an N. And the way we solve for the N is we took the molecular weight, which is 162.23, and we divide it by the empirical weight, 81.13. When we do this, we get a number. It's really like 1.9999, but we round up to the nearest whole number. So here it is 2. What we do with this n is we take the empirical formula and we multiply everything by that n, or 2. And what that does is it gives us this equation, C10, or this formula, H14N2. And this is the molecular formula. It takes a good amount of work to do this, to calculate, use masses to calculate or to show molecular formulas. In class, I will show you another way that you can use to calculate an empirical formula using mass. But to help you practice this, and using all of these steps, again, the more practice you get, the better. I want you to do number 89b and number 99. These will be due September 7th because they will take a little bit more work, and I want to talk to you or to give you the way to solve number 99. So this is a Friday. So you'll have a couple problems due on Wednesday, and you'll have a couple problems due on Friday. But again, to just give you practice on how to do things. The last thing we're going to do has nothing to do with mass, but it does have something to do with moles. We are going to briefly talk about how to balance equations. Many of you have probably had experience balancing equations. Some of you have not. This will be a good review for everyone. The number one rule for balancing equations is do not balance oxygens first. You always save oxygens till the end. Usually they end up balancing themselves. But let's look at a problem that actually does not have oxygen in it. So, dinitrogen tetrahydride decomposes into ammonia or nitrogen trihydride plus nitrogen gas. So the first thing we need to do is we need to account for all of the different elements. So we have N and H. And we have N and H. So we have 2 nitrogens, 4 hydrogens, 3 nitrogens, 3 hydrogens. So when we get to this point, we need to think about how to balance this. So we have 3 and we have 2. What is the common number that 3 and 2 can have? That is obviously 6. So how do we get to 6 nitrogens? Well, if we put a 3 over here, 3 times 2, we'll change this to a 6. 3 times 4, it will also change this to a 12. Okay, so we need to now get 12 hydrogens and 6 nitrogens. So we already have 1 nitrogen here and 2 nitrogens there. How can we get to 6? Well, let's try putting a 4 in front of the ammonia. So now we have 4 times 1 is going to be 4, plus the 2 over here is 6, and then 4 times the 3 hydrogens is going to be 12. If these numbers add up to these numbers, we are now done. Now, for the sake of just an example, let's say we get to balance in this equation and we see something like this. Obviously that's not correct, but just for the sake of illustration, we see a 4, a 6, and a 4. If you end up with that, you obviously know you can divide each one by 2 and still get a whole number. Do that. So it should be 2, 3, 2. It should be the smallest whole number that you can possibly get. So, for practice of these, try number 111, A through D, and turn those in on September 7th, which is that Friday. So this is just this is all of the different calculations that we are going to do in this chapter. However, the ways we can enter into those calculations, the ways we can get mass or moles, or when we learn about combustion, that will change. In class, we will work a few problems with different ways to enter along these paths. I hope this helps. Good luck practicing.